Methodology in Quantitative Research, Part 2. Okay, we're going to start talking about the different types of research designs in quantitative research. As researchers begin to think about how they will want to measure their PICO, they need to ask themselves, will there be an intervention? And what specific design will be used? This is the first step in formulating an idea of what type of design they will pick. There are three types of basic quantitative research designs in a broad sense. Experimental, which is also known as randomized controlled trial, a quasi-experimental, which is the same as experimental but just without randomization, and non-experimental. Now, the second key question the researcher will ask is, well, I will need to have a comparison to my intervention, so what type of comparison will I need? I need a comparison because I need something to measure my intervention against. Now, sometimes comparisons might be utilizing the same person, but in a different moment in time, such as a preoperative patient versus postoperatively. Sometimes it's different people. So we will have some of our chosen people receive an intervention, and some will not receive an intervention. The researcher has to think about exactly how these comparisons will be made. So at this point, the researcher has an idea about the type of intervention they will use. Maybe they've also narrowed it down between the three basic broad types of designs: experimental, quasi-experimental, or non-experimental, and then the comparison. So we are well on our way to figure out a design and some parameters for within that design. Okay, now remember when we learned about confounding variables and how those can really muck up a study? Well, the researcher is charged with trying to figure out how confounding variables will be controlled and which confounding variables will be controlled. This seems easy, but it's a lot of work and thought on the part of the research team. They don't want to spend all of this time figuring out all the blueprints for the research and then have a confounding variable sneak its way in and muck up the findings. Now remember, a confounding variable occurs when an investigator tries to determine the effect of an exposure on the occurrence of a disease or other outcome, but then actually measures the effect of another factor, a confounding variable. Now, there are some ways that a researcher can control for confounding variables. First, you can make a list of everything you can think of, and one by one, consider whether those listed items might influence the outcome of your study. Usually, someone has done a similar study before you, so check the academic databases for ideas about what to include on your list. Random samples can help control confounding variables. A random sample is a sample that is chosen randomly. It could be more accurately called as a randomly chosen sample. Random samples are used to avoid bias and other unwanted effects. Of course, it isn't quite as simple as it seems. Choosing a random sample isn't as simple as just picking 100 people from 10,000 people. You have to be sure that your random sample is truly random. In theory, it's easy to understand. However, in practice, it's really tough to perform. A really large population might be all of the people who have had strokes in the United States. Now, that list of participants would be extremely hard to obtain. Where would you get such a list in the first place? You could contact individual hospitals, of which there are thousands and thousands, and ask for a list of patients. Would they even supply you with that information? And if you could somehow obtain this list, then you will end up with a list of 800,000 people, which you then have to put into a bowl of some sort and choose random people for your sample. This type of situation is the type of real-life situation you'll come across, and is what makes getting a simple random sample so hard to undertake. A crossover study or crossover trial is a longitudinal study in which subjects receive a sequence of different treatments or exposures. While crossover studies can be observational studies, many important crossover studies are controlled experiments. Nearly all crossovers are designed to have balance. whereby all subjects receive the same number of treatments and participate for the same number of periods. In most crossover trials, each subject receives all treatments, but in a random order. Homogeneity is another way to control for confounding variables, as we can select a population that is similar, so that there is less chance for an outlier. An example of this is selecting men 50 to 70 years of age for a cholesterol study and excluding men in their teens and 20s that might be at a lower risk for high cholesterol. Matching is a technique used to avoid confounding in a study design. In a cohort study, this is done by ensuring an equal distribution among exposed and unexposed of the variables believed to be confounding. For example, a study to compare two new methods for teaching reading uses a matched subject research program. The researchers want to compare two methods, the current method and a modern method. They select two groups of children and match pairs of children across the two groups according to ability, using the results of their last reading comprehension test. If the researchers wanted to test another method, they would have to find 3 comparable children to compare between the 3 groups. And finally, there are ways to statistically have some control. It is more in-depth than an undergrad evidence-based practice course really needs to deal with, so we'll move on. Okay, the next question a researcher needs to ask is, from whom will critical information be withheld? They need to know this so that bias can be averted. Typically, the researcher themselves is blinded, but not always. Will the folks delivering the intervention be blinded? How about the participants? Who will know, and who will not? Then, they need to ask about time frames. How often will data be collected? Daily, weekly, and so on. For a cross-sectional design, all data is collected at the same point in time, meaning all at once. For a longitudinal design, data may be gathered over years. The researchers also need to think about relative timing, meaning when will information on the variables be collected? If we look back in time to collect data, this is called retrospective. And if we are going to measure in the future, this is prospective. And where will this study take place? Well, this is important because the setting can influence the data sometimes. We need to know if the same room in the same building will be used every time to collect data, or will we be using various sites? Okay, causality. This is sometimes a really tricky concept. Now, many, if not most, quantitative research is all about finding a cause or an effect, meaning the research is trying to find out if something caused the outcome to happen. For example, a chair breaks when you sit on it because it is made of a weak material. The cause was weak material, and the effect was that the chair broke. But remember, cause and effect is not the same as an association, correlation, or relationship. For example, there may be an association or a correlation between getting hit by lightning and walking outside in a storm. But merely walking in a storm did not cause the lightning. There was just some correlation between increasing the risk of getting hit by lightning by actually being outside in it. Correlations between variables show us that there is a pattern in the data, that the variables we have tend to move together. However, correlations alone don't show us whether or not the data are moving together because one variable causes the other. It's possible to find a statistically significant and reliable correlation for two variables that are actually not causally linked at all. In fact, such correlations are really common. Often, this is because both variables are associated with a different causal variable, which tends to co-occur with the data that we're measuring. So let's think about this with an example. Imagine that you're looking at health data. You observe a statistically significant positive correlation between exercise and cases of skin cancer. That is, the people who exercise more tend to be the people who get skin cancer. This correlation seems strong and reliable and shows up across multiple populations of patients. Without exploring further, you might just then conclude that exercise somehow causes cancer. Based on these findings, you might even develop a plausible hypothesis. Perhaps the stress from exercise causes the body to lose some ability to protect against sun damage. But imagine that in reality, this correlation exists in your dataset because people who live in places that get a lot of sunlight year-round are significantly more active in their daily lives than people who live in places that don't. This shows up in their data as increased exercise. At the same time, increased daily sunlight exposure means that there are more cases of skin cancer. Both of the variables, rates of exercise and skin cancer, were affected by a third causal variable, exposure to sunlight, but they were not causally related. Okay, this is a really deep concept, and I urge you to learn more. Google causality versus correlation, and there is a wealth of videos and other websites to help learn this concept. This is where statistical analyses are so important, as well as a solid methodological design and selection of variables. Now, the term counterfactual is what would have happened to the same people exposed to a cause if they simultaneously were not exposed to the cause. Meaning, it is a representation of what would happen if nothing took place. So sometimes we might want to have a control group as the counterfactual of no intervention. We will measure that group and state that this is what would have happened if no intervention had taken place. All right, remember when we looked at different designs for different questions way back during week 2? Well, here we are again. Researchers use different designs for different questions. Now, researchers often choose an experimental design if they have an intervention, because this type of design offers the strongest evidence of whether a cause results in an effect. And this is why randomized controlled trials are on top of the evidence hierarchy. It shows the strongest evidence for cause and effect. So let's dive deeper into each type of design. We will start with experimental design. This type of design uses an intervention. The researcher does something to something. So this might be a medication, a form of therapy, a dressing type, etc. And the researcher will want to use a control group. The control group doesn't receive the intervention, so that we can measure some type of difference between those who received something and those who did not. Again, this is the counterfactual group, the control group. They received nothing or just the standard of care that they were already receiving. And finally, as we talked about earlier, it is important to have randomization of those who might receive the intervention and those who do not. This helps reduce bias and potential confounding variables. All right, so this control group or counterfactual group, they get no intervention or just standard care. Or sometimes they might get an alternative intervention. Now, sometimes this group just gets a placebo, meaning the group may think they are receiving something so that we can measure all potential reactions or effects. Now, there is a psychological phenomenon called the placebo effect, whereas individuals actually have symptoms or effect even though they just received a sugar pill or whatever. We won't go into that for this class. That's beyond our pay grade. But just be aware it can happen. Also, sometimes this group can be placed in a delayed treatment group, meaning they may eventually get treatment after their original treatment group in order to measure the difference. Now, they would no longer be called a counterfactual group at that point. Now, there are some obvious advantages and disadvantages of experiments. The advantages are that they are powerful for detecting cause and effect relationships, right? Yeah, we do an intervention and we measure the effect. Now, the disadvantages can include the intervention not really being ethical. We are in unique times right now where the COVID vaccine is undergoing trials that were sped up, but there are some ethical questions arising from that. And of course, we are more limited in our time to measure true effect, as it is very depending on maturity of the vaccine. And the other issue is something called the Hawthorne effect. And this is when a study participant changes their behavior just from knowing they are in a study. They can be super subconscious, but it also can alter the outcome. We really have to be aware of this, depending on the study. And finally, experiments can really be super expensive. All right, quasi-experiments. Now, these are identical to a regular experimental study, except that they lack randomization. We talked earlier about why this is sometimes a good idea, depending on what we are studying. And there are two main categories of quasi-experimental designs: the non-equivalent control group design, meaning those getting the intervention are compared with a non-randomized comparison group, or within subjects designs, and this means one group is studied before and after the intervention. Now, there are some advantages and disadvantages of quasi-experimental design. They may be easier and more practical than true experiments, but they make it more difficult to infer causality. And usually there are several alternative rival hypotheses for results. Non-experimental design is where the researcher does not control the independent variable. These are often referred to as observational designs. We can still select our groups and measure the dependent variable, but we don't interfere with the independent variable. Commonly, non-experimental studies are purely observational and the results intended to be purely descriptive. For example, an investigator may be interested in the average age, sex, most common diagnoses, and other characteristics of pediatric patients being transported by air. They may be interested in the prevalence of a clinical presentation pattern or a specific symptom for a given disease. In such studies, the research question would be focused on prevalence rates or such rather than causality. They may propose some associations but cannot effectively statistically support them. A correlational study is a type of research design where a researcher seeks to understand what kind of relationships naturally occurring variables have with one another. In simple terms, correlational research seeks to figure out if two or more variables are related, and if so, in what way. Here are some examples of correlational studies or questions such studies may seek to answer. Someone may want to find out if drinking while pregnant is associated with an increased risk of depression for the teenage child. Or, is smoking associated with Alzheimer's disease? Or, are child victims of abuse more likely to become abusers themselves? A prospective study is a longitudinal study that follows over time a group of similar individuals who differ with respect to certain factors under study to determine how these factors affect rates of a certain outcome. For example, one might follow a cohort of middle-aged truck drivers who vary in terms of smoking habits to test the hypothesis that the 20-year incidence rate of lung cancer will be highest among heavy smokers, followed by moderate smokers, and then non-smokers. In a retrospective design, we look at individuals that share a common exposure factor, and they are compared with another group of equivalent individuals not exposed to that factor to determine the factor's influence on the incidence of a condition such as a disease or death. Descriptive research is defined as a research method that describes the characteristics of the population or phenomenon studied. This methodology focuses more on the what of the research subject than the why of the research subject. For an example, an apparel brand that wants to understand the fashion purchasing trends among New York buyers will conduct a demographic survey of this region, gather population data, and then conduct descriptive research on this demographic segment. The study will then uncover details on what is the purchasing pattern of New York buyers, but not cover any investigative information about why the patterns exist. Because for the apparel brand trying to break into this market, understanding the nature of their market is the study's objective. The advantages and disadvantages of non-experimental research includes: it doesn't yield persuasive evidence for causal inferences. Now, this is not a problem when the aim is description, but correlational studies are often undertaken to discover causes. The advantage is that it is a really efficient way to collect large amounts of data when intervention and/or randomization is not possible. And finally, The overall characteristics of a good quantitative research design include statistical conclusion validity, meaning that it has the ability to detect true relationships statistically. Internal validity, which is the extent to which it can be inferred that the independent variable caused or influenced the dependent variable. External validity, which again is the generalizability of the observed relationships across samples, settings, or time. And lastly, construct validity, the degree to which key constructs are adequately captured in the study. And that is it for part 2 of quantitative methodology.